This video will give you more information about ANOVA and effect size. So for ANOVA or any statistical test, you have these four pieces that work together to come together to give you a statistical conclusion. And these four have to be in balance and work together so that you have confidence in the statistical conclusion. So you have the sample size, which is the number of cases or units or people or participants that you have within your data set. Your effect size is really about practical significance and the thinking about even if you have statistical significance, is your result practical in the sense of the outcome units make sense. So is there enough of a change with the outcome units to make it a practical action item? And then you have your alpha level or your significance level, which you set prior to running your statistical analyses. And we tend to use 0.05, but you could also use 0.01 or 0.001. And this is that number that you compare your p-value to identify statistical significance. And then we have the power. And the power are how likely or what is the probability that you will see an effect, and a statistically significant effect. And power is related to confidence intervals and how likely you are to see a result that is statistically significant for the majority of your distribution or your sample. Effect size is evaluated after you've gotten statistical significance. And so it's used in association with the interpretation of statistically significant results. And so effect size is really looking at how you could look at it as how false your null hypothesis is, or how true is the interpretation or the results that you've received. And I like to think about effect size as practical significance. And so it's like how big is the difference, if we're speaking about ANOVA, how big is the mean difference between groups, and is that mean difference big enough to justify taking action? So if you're looking at like two different treatments and a control, and you find that one of the treatments has a statistically significant mean difference from the other two groups, you have to then look at, okay, is that difference big enough to take action to put that treatment into place for everybody, to spend the money to do that, to set it up, and all of that. And so effect size is really important, especially when we're thinking about analysis of variance and doing mean comparisons across groups, in thinking about next steps and making your results actionable. So there are a number of different effect size formulas, and really you know how to choose the effect size formula you should use based on the context. But this context can be the industry in which the research is being conducted, or this analysis and its results are being used. It also can be the topic area. It also can be with a particular set of participants. So what you typically have to do is you have to understand within the industry in which you're working, what is the appropriate effect size to use, and how best to use that effect size to add to that interpretation of your ANOVA results. So in order to know what an ample effect size would be for you, so each of the effect size formulas usually breaks down the scale of what would be considered small, medium, and large effect size. And it's based on the calculation of that effect size using any particular formula. But you also have to remember the context. So you have to take this small, medium, and large scale and couple that with the context, and you could come up with both of those using the literature, using any of the information given about the effect size, and also how that effect size is used with your FRT statistic. But you could also use um, information about the context to help you figure out what the small, medium, large should be, or what is an ample effect size. So understanding your context can really help you know, even if it's a medium effect size based on the scale, it may not be large enough practically to elicit action. Most commonly for ANOVA analyses, where you're using an F ratio or and an F distribution statistic, we usually are using eta squared, epsilon squared, or omega squared. But again, which of your effect size formulas you use is all based on the context and the industry in which the research is being conducted. The one thing that's the similar for all effect sizes is all effect sizes are going to be between 0 and 1, and they will be split into small, medium, and large. And that's either based off of the formula in which you use, your context, or both. So here are the formulas for the three most common effect sizes used in ANOVA. And one thing you should notice is how they're all utilizing these sum of squares, and in some cases the mean squared values. So you can see that these variance calculations are still being used here as well to figure out the effect size. And so this is another reason why effect size is so important to include with your interpretations of your ANOVA results, because they're both going to be using your variance and the shift and changes in variance for their calculations of results. Another thing to realize for these three most common effect sizes used for ANOVA is that as your sample size gets bigger, they all essentially become the same value. And so then there's not as much reason to really decide or use specific effect size formulas except for the context in which you're working. Um, and so it's really making sure that you understand that yes, you have to pay attention to the calculation of the effect size and how it's determined, also in relation to your context, but then also in relation to your sample size. And so then the other thing is this eta squared is very close to looking at r squared, or is very similar to the calculation of r squared that's used in regression. So while eta squared is nearly equivalent to r squared, epsilon squared is nearly equivalent to the adjusted R squared. And so you have to remember the difference between this R squared and adjusted R squared. Is adjusted R squared is accounting more for the error that is occurring when you're doing that comparison between your expected and your observed. And so because this epsilon squared is really accounting more for this error, it is considered to be the least biased of these three most commonly used. Um, and we know that if eta squared is working similarly to r squared, that it's usually more positively biased, where it makes the results look better than they actually are. But this also is associated with very small sample sizes. So while you have these effect sizes that are most commonly used and most commonly used for a number of different reasons, you also have effect sizes that are used for comparisons. So if you're trying to compare one set of ANOVA results to another set of ANOVA results, you could compare the effect sizes in this way as like usually as proportions to be able to determine which of the study's results are actually more practical or more actionable, depending again on the industry in which the research is being conducted, as well as the context in which the research is being conducted. So there are some general rules of thumb for each of the effect size formulas. Um, but for some of the most common ones, they are here. But all of your effect sizes, you should be able to denote some thresholds of what is considered small, medium, and large, and be able to relate that to the context to determine if that effect size is ample enough in order to make your results actionable. Lastly, here is one of the most commonly used effect size references, especially when using one of the major three effect sizes for one-way ANOVA or really any ANOVA analysis.